Galaxies spin so fast they should tear themselves apart. This simple observation challenges our basic understanding of gravity. For decades, astronomers have been intrigued by why galaxies rotate faster than expected. We will explore the deep implications this holds for dark matter, the nature of space-time, and the long-term story of the cosmos. By the end, you will grasp one of the great mysteries in modern science and how its resolution may reshape our view of reality. We will investigate whether an unseen cosmic presence binds everything together, or if our physical laws need rethinking. What does it mean that so much of the universe could be composed of something beyond our vision? The stars themselves were telling a secret. In the 1970s, astronomer Vera Rubin began a careful study of spiral galaxies, charting how fast stars moved at different distances from the bright central core. She anticipated a familiar celestial rhythm, the same one governing our solar system, where distant planets like Neptune crawl along their orbits while inner worlds like Mercury race around the Sun. According to this logic, stars on the outer edges of a galaxy, far from the central pull of its visible mass, should be moving much more slowly than those closer in. Yet her observations revealed something entirely different and deeply puzzling. The outer stars were not slowing down at all. They were traveling through space just as fast as their inner neighbors. This created what astronomers call a flat rotation curve, a graph line that stays stubbornly level instead of falling steeply away. It was a result that defied the basic laws of gravity as we understood them. The only way to explain how those distant stars could move so rapidly without flying off into the void was if there was a tremendous amount of unseen matter throughout the galaxy, creating a far stronger gravitational pull than the stars and gas we could observe. Vera Rubin's meticulous work provided the first robust evidence that what we detect in the cosmos is only a fraction of what is truly there. Her discovery forced science to confront a profound and invisible reality, a hidden architecture holding the universe together and setting the stage for a mystery that would reshape physics itself. This flat rotation curve is the ghost in the machine of modern cosmology. To truly appreciate its surprising message, picture a simple graph. On one axis, you have the distance a star is from the galactic center. On the other, you chart its orbital speed. In a system ruled only by the matter we can see, the stars and the glowing gas, this graph should tell a very specific story. It would rise quickly near the bright core where gravity's pull is strong, then fall away just as steeply in the outer regions. Think of our own solar system, a miniature model of orbital mechanics. Mercury, close to the Sun's immense gravity, whips around at a blistering pace. Neptune, far out in the cold depths, moves along its orbital path at a much slower rate. This is the predictable rhythm we expected entire galaxies to follow, but the observed data paints a completely different picture. The graph line does not fall. Instead, it stays stubbornly, remarkably flat. Stars tens of thousands of light years from the center, in regions that should be dark and gravitationally quiet, are moving through space just as fast as the stars near the brilliant core. It is as if every planet in our solar system, from Mercury to Neptune, orbited at the exact same speed. This simple, flat line on a graph is the quiet signal that has been echoing through astronomy for decades. It tells us that something is deeply incomplete with our inventory of the cosmos. Either our understanding of gravity itself needs refinement on these vast scales, or the galaxies are filled with a form of matter that does not emit, absorb, or reflect any light, a hidden substance whose gravitational influence is the only sign of its profound presence. This single difference between prediction and observation sparked a conversation that would reshape the field of physics. inviting us to reconsider our most basic ideas about the universe. Sir Isaac Newton gave us a universe governed by elegant and predictable rules. An apple falls from a tree, and the moon orbits our planet, all guided by the same invisible force of gravity. For centuries, his laws of motion and universal gravitation have been our trusted guide to the cosmos, perfectly predicting the graceful dance of planets within our solar system. Yet when we take these same time-honored equations and apply them to the scale of an entire galaxy, something unexpected happens. The math simply does not hold together. According to Newtonian physics, the orbital speed of a star should be determined only by the mass that lies inside its path around the galactic center. As you move outward with more and more of the galaxy's mass behind you, the gravitational pull should weaken considerably and your speed should drop. It is a straightforward and logical prediction, but the starlight tells a different story. By measuring the Doppler shift of that light, which reveals how fast stars are moving toward or away from us, astronomers found the calculated velocities were far, far lower than the speeds they were actually recording. This was not a small rounding error or a minor miscalculation. It was a fundamental mismatch, a deep crack in the foundation of classical physics. The universe was behaving in a way that our most trusted laws could not explain. This clear contradiction forces a difficult choice. Either our understanding of gravity, a force we thought we knew intimately, is profoundly incomplete on the vast scales of galaxies, or we are missing the vast majority of the universe's mass, a hidden component whose gravity is the only clue to its existence. It is a moment where comfortable certainty gives way to a more radical and thrilling truth. Faced with this fundamental mismatch, a profound question emerged. If the mathematics was correct but the universe refused to comply, what was the missing piece of the puzzle? The answer scientists began to propose was as simple as it was radical. What if the galaxies we see are not the whole story? What if every spiral, every island of stars, is merely the luminous core of something far larger and completely invisible? This was the birth of the dark matter hypothesis, the idea that galaxies are embedded within immense, shadowy halos of a substance that does not emit, absorb, or reflect any light at all. This mysterious material would provide the crucial extra gravitational glue, pulling on the outer stars and whipping them around at those unexpectedly high speeds, all without breaking the established laws of physics. The concept was not entirely new. Decades earlier, an astronomer named Fritz Zwicky had observed entire clusters of galaxies moving in ways that suggested they were held together by some unseen, dominant mass. He called it Dunkelmaterei, dark matter. At the time, his idea was largely set aside, a curious footnote, but Vera Rubin's precise data on individual galaxies brought the concept roaring back to life, giving it a solid, observational foundation that could not be ignored. The hypothesis gained even more power with the rise of computer simulations. When scientists modeled the evolution of the cosmos, they found that a universe filled with this strange, invisible matter produced galaxies that looked remarkably like our own. This dark material would not behave like the ordinary atoms we know. It would not collapse to form stars or planets. Instead, it would form vast, diffuse clouds, a cosmic scaffolding upon which the bright structures of the universe could slowly assemble. Its gravity would be the invisible hand sculpting the cosmos and dictating the very speed of a galaxy's spin. This was the elegant, if unsettling, solution. The ghostly halo, not the shining stars, was the true master of the galactic dance. But what if the solution was not to add something invisible to the universe, but to rewrite the rules themselves? This is the provocative path taken by an alternative idea known as modified Newtonian dynamics, or MUND, proposed by physicist Mordechai Milgrom in the 1980s, MUND presents a radically different answer to the rotation mystery. It suggests that our understanding of gravity itself is incomplete, not our census of cosmic matter. Milgrom's theory posits that Isaac Newton's laws, so reliable here in our own solar system, begin to break down when the force of gravity becomes incredibly weak. This happens not at great distances, but at extremely low accelerations, the kind experienced by stars drifting in the lonely outskirts of a galaxy. In these quiet, dark frontiers, MUND proposes that gravity begins to behave differently, providing a subtle extra tug that mimics the gravitational effect of a vast halo of dark matter. It is as if the rules of the game change when the playing field becomes too faint and spread out. This single, elegant modification to the laws of physics allows MUND to predict the flat rotation curves of many galaxies with striking accuracy, all without needing a single particle of unseen substance. For its supporters, this is a more parsimonious solution, one that fixes the problem by refining a fundamental force rather than populating the cosmos with ghosts. Yet this elegant idea is not without its own profound challenges. While it excels at describing the behavior of individual galaxies, MUND has struggled to explain the full tapestry of cosmological evidence. Observations of colliding galaxy clusters, the precise patterns of the cosmic microwave background, and the very large-scale structure of the universe all seem to require the presence of some form of dark matter to be fully understood. This leaves us at a fascinating philosophical crossroads. Do we accept the existence of an entirely new form of matter that makes up the vast majority of the cosmos, a substance that has so far eluded every attempt at direct detection? Or do we take the bolder step of rewriting the laws of gravity, a foundation of physics that has stood for centuries, accepting that it fails us on the grandest scales? The answer will not come from theory alone, but from an ongoing conversation with the cosmos, as we gather ever more precise data to test these two competing visions of reality. This cosmic rotation puzzle does not look the same in every corner of the universe. The subtle influence that guides a galaxy's spin leaves different impressions depending on the type of galaxy we observe. Spiral galaxies, like our own Milky Way with its elegant pinwheeling arms, present the classic case. Here, the flat rotation curve is most clearly defined, with stars at the very edge of the luminous disk maintaining the same high orbital speeds as those near the brilliant core. It is the perfect signature of an unseen force at work. But what about the vast, roundish blobs of stars known as elliptical galaxies? These systems lack the organized spin of their spiral cousins, so astronomers cannot simply chart a rotation curve. Instead, they measure the random, jostling motions of stars within the galaxy. The speeds of this stellar dance are far too great to be explained by the gravity of the visible stars alone. Even in these seemingly placid islands, a hidden mass must be present, acting as a gravitational anchor to keep the stars from flying apart. Then there are the dwarf galaxies, the small, faint satellites that often orbit larger ones. These present a paradox that deepens the mystery. In many of these diminutive systems, the rotation curves suggest that dark matter makes up an even larger fraction of their total mass than it does in grand spirals. They appear to be dominated almost completely by this invisible substance, with the few stars we see merely tracing the outline of a much larger, unseen presence. Most puzzling of all are the recently discovered ultra-diffuse galaxies. These are ghostly giants as large as the Milky Way, but with so few stars they are almost transparent. Their faint light suggests there is very little ordinary matter present, yet their stars move at speeds that indicate a tremendous amount of mass. This creates an incredibly high mass-to-light ratio, a property that challenges both leading theories. For dark matter models, it is difficult to explain why so much dark matter gathered with so few stars. For modified gravity, the extremely weak gravitational fields in these galaxies push its predictions into uncharted territory. By studying this entire family of galaxies, from majestic spirals to faint dwarfs, astronomers are conducting a grand natural experiment. Each type provides a unique test, a different set of conditions against which we can check our ideas. The question is whether a single solution, be it an invisible particle or a revised law of gravity, can account for the rotational behavior of every single one. So how do we actually measure the spin of something as vast and distant as a galaxy? The answer lies in decoding the subtle messages carried within its light. Astronomers use a powerful technique called spectroscopy, which acts like a cosmic speed gun. By carefully analyzing the spectrum of light from a star or a cloud of gas, they can identify specific chemical signatures, dark lines imprinted by elements like hydrogen or calcium. If the galaxy is rotating, one side will be spinning toward us while the other side spins away. This motion stretches or compresses the light waves, a phenomenon known as the Doppler shift. Light from the side moving toward us is squeezed, shifting it slightly toward the blue end of the spectrum. Light from the receding side is stretched, shifting it toward red. The degree of this shift is directly proportional to the speed. By meticulously measuring this cosmic red and blue blush across a galaxy's face, astronomers can chart its rotation, translating the subtle color changes into a precise map of velocity. But starlight only tells part of the story. To probe the darkest, outermost regions where stars are scarce, scientists turn to radio telescopes. These instruments listen for a very specific signal, the 21-centimeter emission from vast, cold clouds of neutral hydrogen gas. This faint radio whisper can be detected far beyond a galaxy's visible edge, allowing researchers to trace the rotation curve to distances that would otherwise be completely dark to us. The results consistently show that even in these remote galactic frontiers, the gas is still moving at unexpectedly high speeds. Technology has since advanced to give us an even clearer picture. Instruments known as integral field units, mounted on giants like the Very Large Telescope in Chile, can capture thousands of spectra simultaneously. Instead of studying one point at a time, they create a rich, detailed velocity map for an entire galaxy in a single observation, painting a dynamic portrait of its spin. And there is one more, entirely independent method that confirms the need for extra mass gravitational lensing. The immense gravity of a foreground galaxy can act as a lens, bending and distorting the light from a more distant object behind it. By analyzing the pattern of this distortion, scientists can weigh the foreground galaxy directly, measuring its total gravitational pull. These measurements consistently reveal far more mass than the visible light accounts for. Each technique, from the classic Doppler shift to the geometry of bent light, arrives at the same compelling conclusion. The unusual rotation is not an artifact of a single method. It is a robust, repeatable signal, a fundamental feature of the cosmos that our instruments continue to confirm with ever greater precision, guiding us steadily toward a deeper explanation. These cosmic clues from starlight and gravity find a powerful echo inside our own machines. Modern supercomputers offer a unique kind of laboratory, one where we can build entire universes from scratch. By programming the fundamental laws of physics into these vast digital realms, scientists can watch cosmic history unfold over billions of virtual years. This process of simulation has become one of the most critical tests for the dark matter hypothesis. When a simulation runs with only the ordinary matter we see, the results are galaxies that look nothing like our own. They form slowly, with stars scattered in disorganized blobs, and their rotation curves are a mess. The outer regions spin far too slowly, completely failing to capture the flat, swift motion we observe through our telescopes. These virtual universes, built on familiar physics alone, simply do not work. But then, a single ingredient is added to the recipe, an invisible component known as cold dark matter. According to the leading model called lambda cold dark matter, this mysterious substance is cold, meaning its particles move slowly, and it does not interact with light or even with itself. When this dark component is included, the simulation transforms. A cosmic scaffolding emerges first, as dark matter condenses into vast, intricate webs and halos under its own gravity. These halos act as gravitational anchors, creating deep wells of attraction. Only then does the ordinary matter, the gas and dust we are made of, begin to fall into these pre-existing wells. As it pools and cools, it ignites into stars, eventually assembling the beautiful spiral and elliptical galaxies that match our real-world observations. The rotation curves of these virtual galaxies are flat, just like the ones Vera Rubin measured. Their sizes, shapes, and distributions across the simulated cosmos align stunningly well with the data from our most powerful sky surveys. This success is profound circumstantial evidence. It suggests that if dark matter exists as the model proposes, then the universe we see is a natural and expected outcome. Yet the picture is not perfectly clear. Some of the most sophisticated simulations still struggle to replicate the exact number and properties of small satellite galaxies orbiting large ones like our Milky Way. Others produce galaxies whose central regions are denser than what we observe. These lingering discrepancies are not seen as failures, but as vital clues. They push scientists to refine the properties of the hypothetical dark matter particle, or to consider whether ordinary matter, through complex processes like supernova events, plays a more dynamic role in shaping galaxies than we thought. The very existence of these puzzles keeps the door open for alternative ideas, reminding us that our journey to understand the cosmos is a conversation, a constant process of testing our most cherished theories against the unyielding evidence of the stars. So these immense halos are the true architects of the cosmos. They are not just a faint, formless cloud. Think of a galaxy not as a simple disk of stars, but as a luminous city built at the heart of a vast, invisible mountain range. The shining city is all we can see, but it is the gravitational terrain of the hidden mountains that dictates the flow of traffic, the speed of every star and every gas cloud moving through the streets. This is the role of the dark matter halo. It forms a roughly spherical distribution, a colossal sphere of unseen particles that completely envelops the visible galaxy, extending hundreds of thousands of light years beyond its brightest stars. Its density is not uniform. It is thickest and most concentrated at the very center, and then it gradually thins out into the cosmic void. This specific density profile is the key to the flat rotation curve. As a star orbits farther from the galactic center, it is no longer governed only by the mass of the inner stars. It is now feeling the collective gravitational pull of this entire, immense halo. Even far out in the darkness, the sheer volume of this invisible structure provides enough gravitational grip to keep the star moving at a high speed, preventing it from slowing down as expected. The story of these halos begins not with the first stars, but long before them. According to our best models, dark matter began to gather together first in the early universe, forming a cosmic skeleton of these halos while the ordinary matter was still a hot, formless soup of particles and light. This invisible framework provided the gravitational wells, the ready-made foundations, into which ordinary gas could eventually settle, cool, and finally ignite into the galaxies we see today. Without this pre-existing scaffolding, the universe would look utterly different, a formless sea of dim, scattered stars. Yet for all their importance, the precise nature of these halos remains a mystery. Are they perfectly smooth spheres, or are they textured, filled with countless smaller subhalos, the echoes of ancient, assimilated dwarf galaxies? Their exact shapes and internal structures are active frontiers of research, with astronomers using the subtle motions of stars and the gentle distortions of gravitational lensing to map the invisible geography of these dark mountains. Every new observation refines our picture, helping us understand the silent, dominant force that guides the spin of every galaxy. The silent architecture of dark matter reveals itself through more than just galactic spin. Another powerful line of evidence comes from the immense gatherings of galaxies known as clusters. These are the largest gravitationally bound structures in the universe, and their sheer mass warps the fabric of space-time around them. This warping acts as a natural lens, bending and magnifying the light from even more distant galaxies lying far behind the cluster. By studying the intricate patterns of this distortion, a technique called gravitational lensing, astronomers can essentially weigh the cluster. The result is always the same. The total mass required to create such a lens is vastly greater than the combined mass of all the galaxies and hot gas we can detect. Once again, an immense, unseen presence makes its gravitational influence known. Perhaps the most dramatic demonstration of this separation came from a system known as the Bullet Cluster. This is not a single galaxy, but the aftermath of a vast collision between two entire galaxy clusters. During such a cosmic event, the different components behave in telling ways. The clouds of hot, ordinary gas detected by their X-ray emission slam into each other and slow down like two clouds of smoke colliding. But the dark matter, which does not interact with itself or the gas, is expected to pass right through the event. By mapping the mass using gravitational lensing, astronomers found that the peak of the total mass, the gravitational potential, did not align with the peak of the ordinary matter. The bulk of the mass had indeed sailed ahead, leaving the lagging gas behind. This was a crucial observation because it suggested dark matter is not a modification of gravity, but a physical substance, a cloud of particles that can be separated from the ordinary atoms we know. The case for this mysterious component is further sealed by looking back to the very beginning of the universe. The afterglow of the Big Bang, known as the cosmic microwave background, is a snapshot of the cosmos when it was just 380,000 years old. Minute variations in this ancient light, meticulously mapped by missions like Planck, form a detailed cosmic fingerprint. The precise patterns of hot and cold spots tell us exactly what the universe is made of. The calculations are stunningly precise, revealing that dark matter makes up about 27% of the cosmos, while the ordinary matter of stars, planets, and everything we see constitutes less than 5%. This means for every ounce of visible reality, there are over 5 ounces of this invisible substance woven through space. These independent lines of evidence, from the distorted light around galaxy clusters to the pristine echo of creation itself, all point toward the same profound conclusion. The gravitational patterns we see are not isolated quirks. They form a consistent, cross-checked picture of a universe dominated by a material that is fundamentally different from our experience. We can map its gravitational shadow with incredible accuracy, yet its true identity remains one of the most profound puzzles in all of science. We know what it does, but we still do not know what it is. So what would this invisible cosmic substance actually be? If dark matter is real, it must consist of some kind of particle, something fundamentally different from the protons, neutrons, and electrons that build our world. Theorists have proposed a whole zoo of exotic candidates to fill this role. For decades, the leading contender has been a class of particles known as WIMP, an acronym for weakly interacting massive particles. As the name suggests, these hypothetical entities would possess significant mass, but they would be profoundly antisocial. They would feel gravity, and they would interact through the weak nuclear force, one of the fundamental forces governing radioactive decay, but they would be utterly blind to the electromagnetic force. This means no light, no reflection, no absorption, no chemical bonds. A WIMP could pass through the entire Earth as if it were not even there, which is precisely why they are so maddeningly difficult to catch. Another fascinating possibility lies at the opposite end of the mass spectrum, the action. This hypothetical particle was first proposed to solve a completely different and highly technical puzzle in particle physics, but it turns out its properties could also make it a perfect dark matter candidate. Actions would be incredibly light, potentially trillions of times lighter than an electron, but they would be produced in such staggering numbers in the early universe that their collective gravity could still dominate. Then there are sterile neutrinos, a heavier, more reclusive cousin of the ordinary neutrinos that flood through space. Or perhaps the answer is not a new particle at all, but countless primordial black holes, tiny remnants forged in the intense turbulence of the Big Bang itself, scattered like invisible gravel throughout the cosmos. The search for these phantoms is underway across multiple frontiers, deep underground, in laboratories shielded from cosmic rays by miles of rock. Incredibly sensitive detectors wait for the rare jolt that would signal a WIMP interacting with an ordinary atom. In space, telescopes scan for unusual X-ray or gamma-ray signatures that could be the final transformation of a sterile neutrino or the decay of an action. And at immense particle colliders like the Large Hadron Collider, scientists attempt to create dark matter in miniature, high-energy collisions, searching for an imbalance in energy and momentum that would reveal something invisible carrying it away. The identification of dark matter would be far more than just solving an astronomical puzzle. It would open a new chapter in fundamental physics, revealing a whole hidden sector of the universe, potentially governed by forces and particles we have not yet begun to imagine. The silent spin of galaxies is not just a question of missing mass. It is a direct invitation to explore a reality that lies entirely beyond our current grasp. Yet for all its explanatory power, the dark matter paradigm is not without its own persistent mysteries. One of the most significant is known as the core cusp problem. Our most sophisticated computer simulations suggest that dark matter halos should have a very specific density profile, forming a steep peak or cusp at the very center of a galaxy. This dense central concentration is a natural outcome of how gravity pulls the invisible particles inward. However, when astronomers study the actual motions of stars and gas within the inner regions of dwarf galaxies, the data often points to a much shallower, more uniform distribution, like a soft core instead of a sharp peak. It seems that in some galaxies, the dark matter in the center is less densely packed than our best models predict. Another major puzzle is the missing satellites problem. Simulations of a universe filled with dark matter produce a very rich substructure. They predict that our Milky Way should be surrounded by hundreds, even thousands, of small, dark satellite halos. Yet when we look, we only see a few dozen small, faint dwarf galaxies. It appears the vast majority of these predicted halos remain completely dark, without a single star to illuminate them. This leads directly to a third challenge, the too big to fail problem. Among the satellite halos that do form in simulations, some are so massive and have such strong gravity that it seems they should easily have attracted gas and formed bright, visible galaxies. The fact that we do not see these expected large, luminous satellites orbiting our galaxy suggests that something is preventing star formation in these seemingly ideal environments, or that our simulations are overestimating their central density. These are not minor issues, they are persistent tensions between the beautiful, clean predictions of the theory and the complex, messy reality of the cosmos. They do not necessarily disprove the existence of dark matter, but they strongly suggest that our understanding of its nature or its relationship with ordinary matter is still incomplete. Perhaps dark matter particles have some small, subtle ability to interact with each other, a property that would smooth out central cusps into cores. Or maybe the explosive feedback from supernova and stellar winds in the early universe blew ordinary gas out of the smallest halos, preventing stars from forming and leaving them dark. These unresolved questions are the vital, driving force behind modern astrophysics. They remind us that a scientific theory is not a finished monument, but a living framework constantly being tested, challenged, and refined by the very universe it seeks to explain. Mund is not the only challenger to the dark matter orthodoxy. Other, more intricate theories of modified gravity have entered the arena, each proposing a different way to rewrite the cosmic rulebook. One such framework is tensor vector scalar gravity, often called TVS. This theory represents a direct and complex extension of Einstein's general relativity. It introduces additional fields alongside the familiar fabric of spacetime, working together to produce a stronger gravitational pull in regions of extremely weak acceleration. The goal is the same as Mund, to explain the rapid rotation of galaxies through a modification of the force itself, rendering the dark matter halo unnecessary. Yet these theories are not mere copies of one another. They diverge in their mathematical foundations and, crucially, in the predictions they make for phenomena beyond galaxy rotation, such as the bending of light by gravity. This gives astronomers multiple ways to test them against the reigning paradigm. An even more radical idea comes from theoretical physicist Eric Verland. His concept of emergent gravity proposes that we have been thinking about gravity backwards all along. Perhaps it is not a fundamental force of nature, but rather a side effect, a consequence of something much deeper. Verland suggests that gravity emerges from the fundamental quantum entanglement of microscopic bits of information that make up spacetime. In this view, the extra gravitational pull we attribute to dark matter is actually a kind of cosmic inertia, a resistance caused by the way dark energy, the force driving the universe's expansion, interacts with visible matter. It is as if the empty space itself pushes back against the stars in a galaxy's outskirts, creating the impression of extra mass. This is a profound shift in perspective, suggesting that the rotation problem is not about missing stuff, but about our incomplete understanding of space itself. Other theorists look not to the quantum realm, but to the geometry of the cosmos for an answer. They explore the possibility that our universe has more than the three spatial dimensions we experience. In these models, gravity could be a force that, unlike the others, is able to extend into these extra, hidden dimensions. On the scale of our solar system, this effect would be negligible. But across the vast expanse of a galaxy, its influence would accumulate, providing the additional gravitational strength needed to bind stars in their swift orbits. All of these alternative approaches share a common philosophical thread, a preference for revising our understanding of a fundamental force rather than filling the cosmos with a substance that has eluded every attempt at detection. They ask whether the simpler solution is to invent a whole new kind of universe, or to finally grasp the deeper laws of the one we already see. The competition is far from abstract. Each theory makes specific, testable predictions about how gravity should behave in extreme environments, from the centers of galaxies to the vast voids between them. This ensures the debate remains a vibrant, driving force in science, pushing our instruments and our intellects to new limits as we listen for the universe's final verdict. Our own galactic home holds its own deep secrets of motion. The Milky Way is not just a distant pinwheel we observe from afar, it is our personal laboratory for this cosmic rotation mystery. From our position roughly halfway out from the brilliant core, we are carried along on a swift journey around the galactic center. The Sun, along with its family of planets, moves at a staggering 220 kilometers every single second, a pace that would take us to the Moon in less than half an hour. This speed alone is not the surprise. The true puzzle emerges when we follow the rotation curve outward, tracking the motion of distant stars and faint hydrogen gas clouds that lie far beyond our own orbit. These remote outposts in the dark and sparse galactic hinterlands continue to race along at speeds that defy the pull of the galaxy's visible stars alone. The only way to explain this persistent, swift rotation is to conclude that our entire luminous galaxy, with its hundreds of billions of stars, is embedded within a far grander structure, a colossal sphere of dark matter. This immense halo is the true gravitational anchor of the Milky Way, containing perhaps 90% of all the mass in our galactic system. We live not just within a disk of stars, but at the heart of a silent, invisible giant whose shape we can only trace through its gravitational influence. Recent data from the European Space Agency's Gaia spacecraft has sharpened this picture with breathtaking precision. By meticulously mapping the positions and motions of over 1 billion stars, Gaia has revealed that our galaxy's rotation is not perfectly smooth and uniform. Instead, the data shows subtle wrinkles and waves in the motion of stars, like ripples on a pond. These irregularities are cosmic fossils, thought to be the lasting imprints of past galactic encounters, moments when smaller galaxies merged with our own, stirring up the stars and shaping the dark matter halo in ways we are only beginning to decipher. These disturbances offer a unique opportunity. They may allow us to map the complex, lumpy distribution of the dark matter itself, understanding not just its total mass but its intricate structure. Studying the Milky Way spin gives us the most detailed map we have of how an invisible presence dictates the dynamics of a galaxy. The patterns we uncover here, in our own cosmic backyard, become the key to understanding the silent rotation of every island universe we see scattered across the deep fields of space. This invisible infrastructure does far more than just guide a galaxy's spin. It fundamentally shapes its entire life story, from its earliest beginnings to its mature form. The solution to the rotation mystery is not a separate detail. It is the very reason galaxies can exist in the rich variety of forms we see today. In the dark matter model, the story of a galaxy begins not with a flash of starlight, but with the quiet, gradual gathering of its dark halo. This halo acts as a vast, pre-assembled gravitational foundation, a deep well of gentle attraction. When ordinary matter, in the form of primordial gas, encounters this unseen structure, it is drawn inward. The gas settles toward the center of the halo, where it can come together, grow dense, and eventually cool enough to ignite into the first stars. The properties of the dark matter halo itself are the primary architect of the resulting galaxy. A massive, slowly turning halo will give rise to a majestic spiral like the Milky Way, its flat disk of stars a direct consequence of the gravitational environment the halo provides. A more varied, lumpy halo might produce an elliptical galaxy, a vast and rounded swarm of stars with little organized rotation. The unseen halo's gravity dictates the final size of the galaxy, the speed of its turning, and even the rate at which it forges new stars. Without this foundational support, our simulations tell a very different story. Attempts to model galaxy formation using only the ordinary matter we see consistently fall short. The gas never settles efficiently into organized disks. The resulting structures are often unstable, with stars moving off on scattered paths or failing to come together into coherent islands at all. The galaxies that do form are faint, irregular imitations of the vibrant spirals and ellipticals we observe. The mysterious flat rotation curve, then, is more than a curious anomaly. It is the most visible sign of a hidden cosmic ecosystem. It is the evidence for the quiet infrastructure that not only spins galaxies faster, but actually enables them to exist in the first place. This relationship helps explain the grand diversity of the galactic population. Why do some galaxies become vast, star-making factories while others are quiet and red, their stellar formation having long since concluded? The answer often lies in the dynamic interplay between the dark matter halo and the ordinary gas within it. A stable halo provides a calm environment where gas can collect and form stars for billions of years. But disturbances, like a meeting with another galaxy, can send ripples through the gas, either prompting a wave of new star formation or gently dispersing the gas away, effectively concluding the galaxy's growth. The rotation we measure today is a single moment in this deep, ongoing relationship. It connects the immediate motion of stars to the billion-year story of cosmic structure, revealing how an unseen presence guides the assembly of the universe's most magnificent islands. The silent spin of galaxies whispers a secret about the entire cosmos. This local mystery of rotation is deeply connected to the grandest scales, shaping the very destiny of our universe. The same unseen presence that keeps stars from flying apart also wrote the blueprint for the cosmic web, that vast, filamentary structure along which galaxies are strung like luminous pearls. The evidence for this is remarkably consistent. The amount of dark matter we infer from galactic rotation curves matches perfectly with independent measurements taken from the faint afterglow of the Big Bang. It is a profound convergence, a single story told by the light of newborn stars and the ancient echo of creation itself. This consistency points to a universe where an invisible substance is the primary architect, a cosmic conductor guiding the growth of structure for billions of years. The implications ripple through every facet of cosmology. The precise nature of whatever force or particle explains the galactic spin directly shapes how we model the universe's expansion. Will the cosmos continue to fly apart, slowed only by the gentle gravitational influence of this dark component? Or could its role lead to a different, more dramatic finale? Our understanding of reality's ultimate fate depends on solving the puzzle in our own galactic backyard. This makes the rotation mystery far more than a curious astronomical anomaly. It is the key that unlocks the narrative of the cosmos from its fiery origins to its distant future, resolving whether we live in a universe filled with invisible matter or governed by revised laws of gravity is not just a technical debate. It is a fundamental step in answering humanity's oldest questions about where we came from, what the universe is made of, and how the story ultimately concludes. The next generation of cosmic observation is already underway, promising to transform this enduring mystery into a solvable puzzle. New facilities are coming online, each designed to probe the rotation problem from a different and powerful angle. The Vera Rubin Observatory, poised high in the Chilean Andes, will perform an unprecedented digital sky survey. Its immense camera will not simply take pictures. It will measure the rotation curves for millions of galaxies, building a statistical map of galactic motion on a scale we have never before attempted. This vast dataset will reveal subtle patterns and exceptions, showing us whether the flat rotation curve is a universal rule or if it has hidden variations that could point toward a deeper truth. Meanwhile, the James Webb Space Telescope peers back in time, its infrared gaze piercing through cosmic dust to witness galaxies in their infancy. By studying how the earliest structures began to spin, Webb can test whether dark matter halos were indeed the foundational seeds, as the leading theory suggests, or if the dynamics of young galaxies tell a different story entirely. Here on Earth, the search becomes deeply personal and incredibly delicate. In former gold mines and deep beneath mountains, experiments like LZ and Xeno-NNT wait in profound silence. Their ultra-pure detectors, shielded from nearly all interference, are designed to feel the faintest whisper, the minuscule jolt of a single dark matter particle interacting with ordinary matter for the first time. A single confirmed signal from one of these tanks would instantly solve the mystery, transforming dark matter from a theoretical ghost into a tangible substance we can finally begin to understand. But if these detectors continue to find nothing, the case for modified gravity grows stronger. From the silent vacuum of space, the Euclid spacecraft adds another crucial layer. It is creating a giant map of the dark universe, not by looking at rotation, but by watching how the gravity of unseen matter bends the light from billions of distant galaxies. This grand census of cosmic distortion will reveal the precise distribution of dark matter across the universe, testing whether its gravitational pull aligns perfectly with the motions of stars within galaxies, or if there is a subtle disconnect. On the horizon, colossal radio telescopes like the Square Kilometre Array, or SCAR, will listen to the universe with unmatched sensitivity. They will trace the faint radio signature of neutral hydrogen gas in galaxies to their very outermost fringes, charting rotation curves with a precision that feels almost like touching the stars themselves. All of this data feeds back into increasingly sophisticated computer simulations, virtual universes where physicists can test the most subtle properties of dark matter particles or the most complex formulations of modified gravity against the hard, unyielding evidence of the real cosmos. The answer to why galaxies spin so fast may not arrive with a single dramatic announcement. It is more likely to emerge gradually as these independent lines of inquiry converge, each one narrowing the possibilities until only one compelling explanation remains. The solution could come from a flash of light in a deep underground tank, a new wrinkle in a billion galactic rotation curves, or a pattern in the ancient light of the early universe that no one anticipated. This search for an answer is as much a philosophical journey as a scientific one. At its core, the galactic rotation mystery asks a deeply human question: how can we know something we cannot see? Every piece of evidence for the unseen, whether it points to a dark matter particle or a revised law of gravity, is fundamentally indirect. We are inferring the existence of an entire cosmic reality based solely on its gravitational shadow, its subtle pull on the things we can observe with our telescopes. This process of reasoning from effect back to cause is a powerful tradition in science. History is filled with examples of brilliant minds proposing the existence of invisible entities long before technology could confirm them. The ancient Greeks speculated about atoms, tiny, indivisible bits of matter, centuries before we could image them. Scientists once theorized about black holes, regions of space where gravity is so intense that not even light can escape, purely through mathematical equations, long before we captured their haunting silhouette. In each case, the idea preceded the proof, guided by a trust in the consistency of natural laws and the power of logical inference. The current debate sits squarely in this tradition. We are presented with two compelling, yet fundamentally different, paths to explain the same celestial phenomenon. One path populates the cosmos with a new kind of substance, an invisible architecture that makes up the vast majority of matter. The other path suggests we must rewrite the rules of gravity, one of the most trusted forces in physics. This choice represents a classic tension in how science progresses. Does nature favor simplicity in its fundamental constituents, meaning the universe is mostly made of stuff we have not yet identified? Or does it favor simplicity in its laws, meaning we should adjust our equations before inventing a whole new form of reality? How do we decide between two competing explanations when both can, with some tuning, account for the rotation curves we measure? The resolution often comes not from reanalyzing old data, but from finding a new kind of observation, a crucial test that one theory predicts and the other cannot easily accommodate. This is why the search has expanded to galaxy clusters, the early universe, and delicate laboratory experiments. We are seeking that one piece of the puzzle that fits perfectly into only one of the competing pictures. These philosophical layers remind us that the greatest cosmic mysteries do not just challenge our instruments, they challenge our very mode of thinking, pushing us to question how we know what we know and forcing us to hold multiple, contradictory possibilities in our minds until the universe itself points the way forward. A playground merry-go-round offers a surprisingly accurate model for this galactic mystery. Picture children clinging to its spinning platform. Those holding on near the center have a relatively slow, gentle ride. But the children at the very edge are whipped around at a thrilling, dizzying speed, fighting centrifugal force to keep from flying off. This is exactly what Isaac Newton's laws predict for a galaxy, where the central pull of gravity weakens with distance. The stars on the outer edge should be those slow-moving children near the center, not the ones racing wildly at the rim. Yet our telescopes show us that all the stars from the inner core to the distant fringe are moving at nearly the same rapid pace. So how do we explain a galaxy where no one is flung from the ride? The leading solution, dark matter, is like adding invisible ropes pulling outward on every single rider. These ropes provide an extra, unseen force of tension, a gravitational grip that keeps even the outermost stars securely in place, matching the speed of their inner neighbors without any visible means of support. It is a hidden harness ensuring the entire structure spins as a single, cohesive unit. The alternative explanation, modified Newtonian dynamics, changes the rules of the playground itself. Imagine if the physics of the merry-go-round were altered so that the push needed to keep it spinning became easier the farther out you went. The children at the edge would find it requires no more effort to maintain their speed than those in the middle, a subtle change in the fundamental mechanics of motion that naturally results in that flat, uniform spin. These simple analogies are, of course, imperfect. Galaxies are not solid disks, and gravity is not a literal rope. Yet these mental models help translate an abstract mathematical conflict into a tangible, visual problem we can almost feel. They prepare us for the deeper question, forcing us to choose between two very different visions of reality. Do we accept the existence of a vast, unseen harness woven through space, or do we rewrite the instruction manual for motion itself across the cosmos? The history of science is a story of quiet revolutions, moments when the universe politely but firmly declines to follow our rules. Our understanding of gravity itself has been through such transformations before. Isaac Newton's laws were a monumental achievement, a framework so powerful it seemed to describe the cosmos with perfect clarity. Yet when astronomers discovered a tiny anomaly in the orbit of Mercury, a slight wobble that Newtonian math could not explain, it was not the end of physics. It was the beginning of a deeper chapter, Albert Einstein's theory of general relativity emerged from that discrepancy, reimagining gravity not as a force but as the curvature of spacetime itself. It was a breathtaking leap that solved the puzzle and expanded our reality. The mystery of galactic rotation sits squarely in this noble tradition. It is another moment where observation has outstripped explanation, forcing us to look again at our most fundamental assumptions. Vera Rubin's journey with those flat rotation curves is a classic example of this scientific process in action. When she first presented her data, the idea that galaxies were mostly made of invisible matter was met with deep skepticism. It challenged the foundational assumption that what we see is what is there. Yet she persisted, gathering more evidence, building a case so robust that the scientific community had to listen. What was once a radical fringe idea gradually became the leading theory, not through rhetoric but through the relentless weight of data. This is how science self-corrects. It is a system built not on certainty, but on a capacity for change when confronted with a better story supported by evidence. The current debate between dark matter and modified gravity is not a sign of crisis, but a sign of health. It is the scientific method playing out in real time. Competing theories are making specific, testable predictions. Will a direct detection experiment finally register a dark matter particle? Will a new telescope observation of a distant galaxy's spin perfectly match a modified gravity model without any need for dark matter? These are the questions that drive progress. The controversies of today, the ones that fill scientific conferences and spark passionate debates, are very often the settled chapters of tomorrow's textbooks. They represent the growing pains of our collective understanding, the necessary friction that occurs when we push at the edges of the known world. Deep underground, in a silence more profound than any found on the surface, the most patient hunt in science is underway. Laboratories like SNOLAB in Canada, nestled 2 kilometers below the Earth in an active nickel mine, or the Gran Sasso facility in Italy, shielded by a mountain of rock, are humanity's quiet outposts in this search. Their sole mission is to catch a ghost. Within these caverns, scientists deploy incredibly pure and sensitive detectors, often filled with liquid xenon or argon, chilled to extreme temperatures. They are waiting for an event so rare it might happen just a handful of times a year, if at all, the minuscule jolt of a dark matter particle gently bumping into the nucleus of an ordinary atom. This direct detection relies on the slim chance that a WIMP, a weakly interacting massive particle, will transfer a tiny amount of energy as it passes through the detector. The resulting flash of light or ripple of charge would be the first tangible proof of the universe's dominant matter. To have any hope of seeing this whisper, every other form of interference must be eliminated. The immense layers of rock overhead act as a natural shield, absorbing the constant rain of cosmic rays that would otherwise overwhelm the detectors with false signals. The materials used in the detectors themselves are meticulously chosen for their ultra-low radioactivity, because even the faint natural decay of ordinary elements in the surrounding rock or the apparatus would drown out the signal they seek. For decades, these experiments have been growing in scale and sensitivity. While no definitive, confirmed signal has yet emerged, the search has been far from fruitless. Each new, more sensitive run of an experiment like LUX Zeppelin or Xeno NNT systematically rules out vast swaths of possibility. They tell us what dark matter is not, carving away at the theoretical landscape and forcing physicists to refine their models to consider lighter particles or different kinds of interactions. This process of elimination is a crucial form of progress in itself. In parallel, another approach tries to create dark matter rather than catch it. At the Large Hadron Collider in Europe, protons are smashed together at nearly the speed of light, recreating the energetic conditions of the early universe. Scientists meticulously analyze the debris of these collisions, looking for an imbalance. If energy and momentum seem to go missing in the aftermath, it could be carried away by an invisible particle, a dark matter entity produced for a fleeting moment before it escapes the detector entirely. The fact that neither of these monumental efforts has yet delivered a clear signal is not a cause for despair, but a catalyst for creativity. It has prompted theorists to broaden the search beyond the familiar WIMP. Perhaps dark matter is made of actions, particles so light and numerous they behave more like a pervasive field. Or maybe it consists of primordial black holes formed in the first chaotic moments after the Big Bang. Each new candidate suggests a different kind of experiment, a new way to listen for the universe's hidden heartbeat. This multi-front search, from the deep quiet of underground labs to the violent collisions in particle accelerators, represents a collective determination to answer one of science's most profound questions. The continued silence is not an end, but a guide, pointing us toward ever more exotic and subtle possibilities, ensuring that the hunt will continue until the invisible majority of our cosmos finally steps into the light. The distant past holds a crucial key to this spinning mystery. We can now look back in time, using powerful telescopes as time machines to observe galaxies when the cosmos was young. By studying the rotation of these ancient structures, we put our theories to their most severe test. What happens when we observe a galaxy that existed when the universe was only a quarter of its current age? Remarkably, some of these adolescent galaxies already display the same flat rotation curves we see in their modern counterparts. Their outer regions were already spinning far too quickly, a cosmic quirk established incredibly early in the history of everything. This is a profound challenge for some versions of modified gravity. Certain models predicted that in the denser, more compact universe of the past, the modified gravitational behavior would not yet have kicked in, and rotation curves should have looked more normal, sloping downward as expected. The fact that the anomaly appears so soon suggests the invisible hand was already at work. For the dark matter hypothesis, however, this early establishment fits naturally into its narrative. If dark matter halos were the first structures to form, condensing out of the primordial soup just after the Big Bang, then they would have been fully in place, gravitationally shaping the earliest galaxies from their very first moments. The young stars would have simply lit up within these pre-existing invisible scaffolds, their swift rotation a direct inheritance from a dark foundation laid down at the dawn of time. This cosmic archaeology is now reaching new frontiers with the James Webb Space Telescope. Its infrared eyes are uniquely suited to peer through cosmic dust and see the earliest generations of galaxies, some forming when the universe was only a few 100 million years old. By carefully analyzing the light from these infant systems, astronomers are beginning to map their rotation, searching for the moment when the familiar pattern first emerged. Does the rotation mystery stretch all the way back to the very first galaxies, or is there a transitional period where the rules were different? Each new data point from these deep time observations acts like a piece of evidence in a grand cosmic trial, helping to judge which of our competing visions of reality best matches the story written in the stars from the beginning. The mathematical heart of this mystery is surprisingly direct. For any orbiting body, from a planet to a star, its speed is governed by a simple relationship between the gravitational pull it feels and its distance from the center. In a system like our solar system, where the Sun contains almost all the mass, this relationship is clean and predictable. The orbital velocity falls off with the square root of the distance. This means if you move 4 times farther out, you should orbit at only half the speed. This is the rhythm the cosmos taught us to expect. But when astronomers apply this same mathematical logic to an entire galaxy, adding up the gravitational pull of every star, every gas cloud, every speck of dust we can see, the numbers fail dramatically. The calculated speeds for stars in the outer regions come out far, far too low. The predicted velocity curve plummets steeply downward, a mathematical certainty based on the visible mass. The observed curve, however, remains stubbornly, impossibly flat. This is not a minor accounting error. It is a fundamental mathematical contradiction. The universe is providing one answer, and our trusted equations, using only the ingredients we can see, are providing another. This numerical gap is the precise space where the entire debate lies. To make the math work, you must add something to the equation. One solution is to insert a tremendous amount of additional mass, distributed in a specific, invisible halo, whose gravity provides the extra pull to explain the high speeds. The other is to change the equation itself, to propose that the law governing orbital velocity is subtly different on the vast, faint scales of a galaxy. The precise shape of the mismatch is itself a crucial clue. It tells us that if dark matter is the answer, its halo cannot be a uniform blob. It must be denser at the center and gradually thin out in a very specific way to produce that perfectly flat rotation curve. If modified gravity is the answer, the mathematical adjustment must be exquisitely tuned to kick in exactly at the incredibly low accelerations found in galactic outskirts, mimicking the effect of that missing mass. While the full calculations involve complex integrals and detailed models, the core inconsistency is mathematically unambiguous. It is a clear signal that something is missing from our cosmic ledger, a numerical ghost that has driven decades of investigation and forced us to confront the limits of our understanding. This cosmic puzzle reaches far beyond the distant stars and into the fabric of our own society. For anyone who has ever looked up at the night sky and wondered, the mystery of spinning galaxies touches something deeply human. The drive to solve it pushes our technology to remarkable new places, creating tools with unexpected benefits for everyone. The quest to detect an unseen particle has led to revolutionary advances in ultra-pure materials and incredibly sensitive sensors. These innovations are already finding uses in medical imaging and security systems, improving lives in tangible ways. The computational power needed to simulate entire universes has spurred breakthroughs in data processing and complex system modeling, techniques that now help us predict weather patterns and manage global financial networks. Even the advanced optics developed for our largest telescopes are refining laser surgery and high-speed communication. This is how pure curiosity becomes practical progress, building a better future one question at a time. On a deeper level, the rotation mystery challenges our most basic assumptions about reality itself. Are we surrounded by a hidden world, a form of matter that makes up most of everything yet slips through our fingers like smoke? Or are the rules of the universe rules we have trusted for centuries, subtly different than we believed? This is not just an academic debate. It is a profound philosophical inquiry into the nature of existence, inviting us to consider the limits of our perception and the possibility of realities beyond our current grasp. It reminds us that our understanding of the cosmos is still young, filled with magnificent unknowns waiting to be explored. This sense of wonder is a powerful educational force, inspiring young minds to pursue careers in science, technology, engineering, and mathematics. The simple, baffling question of why galaxies spin so fast has launched countless journeys of discovery, cultivating the next generation of problem solvers and innovators who will tackle the great challenges of tomorrow. Culturally, this enduring puzzle serves as a beautiful, humbling reminder of our place in the cosmos. We are a species on a small planet, orbiting an average star in the outskirts of a galaxy that itself is behaving in ways we do not fully understand. Yet our curiosity compels us to reach out, to measure, to question, and to seek answers. The rotation mystery stands as one of science's great open frontiers, a testament to the fact that despite our incredible advances, the universe is still full of secrets. Its eventual resolution will not just close a chapter in astronomy. It will likely open a door to an entirely new realm of physics, revealing facets of nature we have not yet dreamed of, with potential applications that ripple through our technology and our worldview for centuries to come. This makes the search for an answer far more than an academic exercise. It is a fundamental part of our shared human journey to comprehend the magnificent cosmos we call home. The question of galactic spin resonates far beyond the lonely frontiers of astronomy, creating a vibrant conversation across the entire landscape of human knowledge. This is not a puzzle for astrophysicists alone. Particle physicists contribute the exotic candidates for what dark matter could be, designing delicate experiments to catch these phantoms in deep underground labs. Computer scientists build the digital universes inside our most powerful supercomputers, crafting simulations that test how galaxies form and evolve over billions of virtual years. Philosophers examine the very nature of evidence, asking how we can so confidently claim to know something we have never directly seen, simply by observing its gravitational shadow on the cosmos. Mathematics provides the elegant language to describe alternative theories of gravity, offering new equations that might one day rewrite the cosmic rulebook. Engineers are the unsung heroes, creating the immense telescopes that peer back to the dawn of time and the hypersensitive detectors that listen for a whisper in the dark. Even biology enters the discussion, posing a profound speculative question. If dark matter truly is the universe's dominant matter, could its subtle gravitational influence have played any role in the conditions that allowed life to emerge and develop on worlds like our own? This cross-pollination of ideas is a hallmark of the most fundamental scientific challenges. The solution to the rotation mystery will not be found in a single discipline working in isolation. It will likely emerge from the concert of many different fields, a symphony of insight where a breakthrough in a particle collider, a new pattern in a sky survey, or a novel philosophical argument could each provide the crucial piece that finally completes the picture. Our journey through the spinning heart of galaxies brings us to a profound realization. The universe is far stranger and more magnificent than we ever supposed. What began as a simple anomaly in starlight, a flat line on a graph, has blossomed into one of the most compelling mysteries in modern science. We have traced this thread from Vera Rubin's meticulous charts to the quiet depths of underground laboratories, from the vast digital universes inside supercomputers to the pristine echo of the Big Bang itself. This single puzzle, the question of why galaxies spin so fast, has challenged the very foundations of physics, inviting us to consider unseen worlds or perhaps rewritten laws. The implications ripple outward, touching everything from the nature of gravity to the ultimate fate of the cosmos. Whether the final answer involves a halo of dark matter particles, a subtle shift in our understanding of gravity, or a concept we have not yet conceived, one thing is certain. Solving this mystery will not merely fill a gap in a textbook, it will open a door to a new understanding of reality, revealing a deeper layer of the cosmos that has been hidden in plain sight all along. The story of galactic rotation is a powerful reminder that our most basic questions, the ones that arise from simply looking up at the night sky with wonder, can lead to the most profound truths. As this chapter of investigation continues, with new telescopes and more sensitive detectors joining the search, we stand on the threshold of a revelation that will reshape our place in the universe. And when this mystery is finally solved, it will not be an ending, but a glorious new beginning, unveiling fresh questions and even grander mysteries waiting for the next curious mind to explore.